Hello, everyone. We have looked at analyzing systems using the Laplace domain, time domain. We have then developed this method of linearization so we can convert nonlinear systems into linear systems so that we can then apply those techniques. And something I mentioned was that a lot of these techniques are so that we can get the system to behave in the way that we want it to, that is, controls, wherein we have some reference signal that is that this here is how we want our system to behave, something like this, which is basically that your um, whatever is your output variable, let's say your output variable is x of t, and this signal here is called the reference signal. This is what we want our x of t to be. Okay, so this is like, we know that if the system does this kind of behavior, then we are achieving some reward or we are achieving our goal. In reality, the way that the system behaves is most definitely going to be different from this because the system cannot go from 0 to some finite value in 0 time. So in reality, your system might behave perhaps like this, or it may behave like this. Between these two systems, which one is underdamped? The underdamped system would be the one that shows these oscillations. Right, so this here is an underdamped system. This here is an overdamped or critically damped system. Um, in this example, what I was showing was a case where you have a vertically suspended mass spring damper system. You're measuring some x of t here, and you're applying some force f of t. If this force f of t is the same as this reference signal, then you would get a system response. So this is x1 of t, which is the case where this system is underdamped, sorry, critically damped or overdamped. This here is x2 of t. So if you apply your force to be the exact same thing as your reference signal, then of course your system is going to move towards a new equilibrium, but then you take out that force and then it comes back to its equilibrium position. It's the case if C and K are such that the system is critically or overdamped. This is the case if C and K are such that your system is underdamped. Now, in that case, when you suddenly activate a force, the system will rise up and then it'll try to achieve that equilibrium at the new position, with the exponential decay of that exponential term, um, and with the sinusoidal terms here. And you take out the signal, and now from this new initial condition, it's coming back to its 0 position. So you see that oscillation there as well. So essentially what I'm trying to show here is that the dynamics of the system are dependent on the characteristics, a characteristic polynomial. In particular, it's dependent on the poles. So if the poles are such that the system is critically damped or overdamped, it'll be in this way. If it's underdamped, it'll be in this way. Now, what we're trying to achieve with controls is that we want the system to have a response that is identical to this. Well, that may not always be true, but if you change your force so that your system, instead of tracking in this way, it tracks something like this, then you would be able to better achieve your reference signal. Now, how is it that you're going to have your position change in this way? Instead of what I drew here, you'll have to have a much higher force in the beginning, and then that force would gradually reduce so that it can initially ramp it up so quickly and then keep it steady there. And then you'd have to have a force that's going all the way down to bring it down very quickly. In this case, your force would have to have some kind of oscillation so it can remove these oscillating features. But how do we say that the system is achieving any weight? Essentially, two aspects to a control system performance. First one is steady state error. That is, how close is your output? In this case, we've been calling it x1 of t or x2 of t. How close is that to r of t as t tends to infinity? So essentially, I'm going to call it y of t as t tends to infinity. Just so that, it's not just for this system, it's for any system. So y steady state is basically the value of y at infinity. If you're able to apply the final value theorem, then this is limit s tending to 0, s times y of s. Now, to r of t. Now, r of t at t tending to infinity, I'm going to define it as rss is defined as r of infinity. So now the steady state error is equal to the difference between these two. And if I were to define the percentage error, this would be equal to RSS minus YSS over RSS times 100 in percentage. What is this saying? If your R of t, that is your reference value, is at some position R naught, then given enough time, will your Y of t reach that point? That is it going to, so let's draw this dotted line here. Is it going to stabilize at some point here? In which case, going to infinity, you'll still have some error. Or is it going to stabilize at this point? That is your target position. Since this here is RSS, is your YSS equal to that or is it different? It doesn't care about how it achieves it. It doesn't care about whether it overshoots and then stabilizes or it goes straight to that point. It doesn't care about any of that. It only cares about at the time t time to infinity, is there a gap between your target RSS and your YSS? This epsilon error should be equal to 0 if you have great control system performance. That is related to the final outcome given time t time to infinity. There is another aspect, which is the transient behavior. Now, that relates to what happens on the way to getting to that steady state. So, transient behavior, there are two components to it. I'm going to call it transient performance requirements instead of transient behavior because we've studied transient behavior. This is more about defining a control system. So the first part, which I'm going to call 2A, is the settling time. You've seen this word before. It's essentially the settling time for 2%, which is basically when that exponential decay has finished 98% of the decay. This is going to be equal to 4 over zeta omega n if it is second order. What is it for first order? 4 over 1 by tau or 4 tau for first order, right? So how do we define this settling time? Um, let's say for first order, we have real part of S, imaginary part of S, and we just look at where is that the pole. So it will have a point, let's say it's over here. I'm going to define that as minus 1 over tau, simply because if I had to write it as tau s plus 1, x of s is equal to u of s. Now, this here's a characteristic polynomial. S is going to be equal to minus 1 over tau, right? So in this case, your settling time Ts2% is equal to 4 tau, 4 over. In this case, we have the position of the pole as minus 1 by tau, right? That is your pole. 4 over minus 1 over tau. If I were to take the absolute value of that, this gives you the 4 tau that we had derived earlier. Similarly, if it was a second order, and then we had two poles, we're only really looking at the real part. I'm going to say this here is S1, and this here is S2. Which one is the faster dynamic? Which one is the slower dynamic? First, try to recall what is the dominant root. The dominant root is the one that is having a larger real part. So the one that is in this direction, which means this here is a dominant root, right? So this one would be the dominant root, which basically means it has the slower dynamic. What does that slower dynamic mean? This is just a review of what we studied earlier. You'll have two roots. One of it will be decaying slowly and one of it will be decaying quickly. Of course, you're going to multiply some coefficient with this response and then add them up together. This one here will vanish very quickly, while this one will remain. So this is the dominant one. We've seen that it is the one with the larger real part. So essentially, in second order systems, the larger the real part of the pole, the slower the response. And that's kind of how we had gotten to that same 4 over zeta omega n. So in general, we can say Ts2% is equal to 4 over the absolute value of the real part of the larger pole. Okay, of course, this has to be the dominant pole. Okay, this is settling time. There's one more, so 2b, that is the overshoot. We just looked at overshoot some time ago. The overshoot is essentially, we've looked at this, but let's say that you have this here as your target and your system behaves like this. Now, this much is the overshoot. When is that a bad thing? One example of a control system is an elevator or a lift that's taking you from one floor to the other. You want that the lift moves and arrives at the desired destination floor in this manner and without this kind of behavior. Sometimes you might have that your lift will have some overshoot. You might just want it to be manageable, so something like this. It might be imperceivable to a human who's in the lift. So the thing with overshoot is that you want it to be within desired design requirements. Do you remember the equation for overshoot? You don't have to. The equation sheet provides that to you. So you're looking for the case where it's underdamped, which means you're looking for this. And this here is the case of free response. Now we're looking at the case with the force input. What is the percentage overshoot? It's basically given here as 100 e raised to minus pi zeta over root over 1 minus zeta square. So that is your percentage overshoot. You'll have something like, the equation is percentage MP is equal to 100 e to the power minus pi zeta over root over 1 minus zeta square. So a lot of times you'll have something like this has to be less than 0.1%, and then your system is within design requirements. Okay. So let's now just consider the case. And there's a very quick example for how you might design a system. There's like system development. You might know of the Lancet, which is this, it's like a medical device. It's a pen with a little pin inside. And now you press this pen against your skin. And when you pull the trigger, this needle will go and prick the skin and come back out. So it has to prick the skin very precisely, only probably 0.2 millimeters or something like that, and come out. And now from the region of the skin that has been pricked, there'll be a little droplet of blood. You can take that droplet of blood and measure the sugar content. You might be familiar with this kind of blood sampling pen. Okay, so there's an example. Now, the dynamic of the system can be captured using the same spring mass damper system. There is a little pin at the end of this mass, and at SEP, or when it is resting, it's given by y is equal to 0. Well, actually, it will not be the SEP, it's actually loaded. So let's not call it that if it's not it. It's just measuring from some point like this. And then you have this spring and this damper. And you have the skin at this position. So the encasing of the pen holds that distance. So this here is the skin. And what we want is that this y goes into the position y is equal to r naught, and then it comes back out. So this is the desired behavior that you want. It only pricks the skin once. This is y of t. This is t. This here is your r naught, which is your skin position with respect to y is equal to 0. So this is where the pen rests when it has been loaded, and then it will go out and it has to come back in. So if you were to look at the response, it should look something like this. Fix it only once. When it comes to rest, is its true equilibrium, which will actually be here when it is no longer loaded. To say outside the skin. Okay. So here's what is the desired behavior. If you want to write that mathematically, so you can start to develop your control system. You have a desired behavior of the percentage overshoot being less than 9%, and that you have a settling time less than or equal to 0.1 second. So this 9% is how much does this go outside of its from its starting point. And TS being 0.1 is how quickly does it settle to 98% of its final steady state response. So what is a system that meets this? Okay, so the first thing I'm going to define it this way, and this here's the second one. Well, the first one, which is basically saying 100 e to the power minus pi zeta over root over 1 minus zeta square less than or equal to 9. So first, let's do the limit case when it is basically equal to 9. So set this equal to 9 and solve for zeta. You will get zeta is equal to 0.61. Okay. Now, how does that define the region in which it operates? So this was the real part of S, the imaginary part of S. Back in the pole B, based on this, to be able to understand this, let us define a pole that is second order underdamped. So we'll have complex conjugate poles for second order. Why is it second order underdamped? Because when you look at the behavior, you see that there is this overshoot and oscillating behavior that happens in second order underdamped, at least in the cases that we have looked at. What are the roots? Well, it's not provided in the equation sheet, but you can see that it's going to be something in this form, except there's going to be a complex term. Your poles are going to be S1, 2 from, you're essentially starting from x double dot plus 2 zeta omega n x dot plus omega n square x. You're finding the roots of this, so it's going to be s square plus this much times s plus this much. You're finding the root for this to get you s12 is equal to, you will get in the end minus zeta omega n plus or minus j omega n root over 1 minus zeta square. So the poles are going to be having a real part of minus zeta omega n. So this here is minus zeta omega n, and then it'll have the imaginary part as plus j omega n root over 1 minus zeta square and minus j omega n root over 1 minus zeta square. I'm not able to do this. So these are the two poles in a complex conjugate setting for the second order underdamped systems. Um, from this, how do we get to this point that zeta is equal to 0.61? Can you see a zeta here? Like just a zeta in this graph. To analyze it further, okay, let's look at what is the hypotenuse. This hypotenuse has a magnitude of how much? Or essentially, what is the magnitude of the complex pole? You're essentially doing root over this distance plus this distance. Root over square of this distance plus this distance squared. So it is minus zeta omega n squared plus omega n root over 1 minus zeta square whole square under root, which is basically equal to omega n, which means that this distance here is omega n. Now, can you see a way of extracting zeta? Not yet, because there is some theta here that if you now look at cos theta, then you can extract your zeta. Essentially, cos theta is going to be equal to this distance, that is zeta omega n, over omega n. So that is zeta omega n over omega n is equal to zeta. Right? So here now we have something in your S plane that represents just zeta. That's basically cos theta is equal to zeta. So this part here is general for second order underdamped systems, what we've just been discussing. I'm going to box it. And from this analysis, we now have something we can use, which is basically that for the system in consideration, we have cos theta is equal to zeta, which is 0.61, right? So what is that theta? It's 52 degrees. How does that feature in our S-plane graph? I'm actually going to move this to another page. So we have theta is equal to 52 degrees, which means that we now have a system, we have real part of S, imaginary part of S, and we have for the limit case, that is um, when this is equal to 9, we have zeta is equal to 0.61, we have cos theta is equal to 52. Sorry, cos theta is equal to 0.61, giving us theta is equal to 52. So now we have a ray that extends outwards in this way, which represents the case where we consider this pole. Of course, we have the mirror image because always complex conjugate. So we have another one here of 52 degrees. And then here is the region that is defined. So, well, this thing extends to infinity, and this entire region is such that we're satisfying the first performance criteria, which is that your cos theta is equal to zeta as a limit case, and we have everything less than or equal to that covered in this region. Okay. Then comes the second one, which is that we have the settling time less than or equal to 0.1. Now, this is something we just discussed here earlier, which is that the settling time is limit case 4 over the magnitude of the real part of pole. So in this case, what is the magnitude of the real part of the pole? It is, okay, let me write this down formally. Ts less than or equal to 0.1 means 4 over the magnitude of real part of the pole, the dominant pole, which in this case is the same, must be less than or equal to 0.1, which gives me essentially that the magnitude of the real part of the pole must be, is it greater than or less than? It will get greater than or equal to 40. Remember, there's a magnitude of the real part of the pole, which means that if I were to sketch this and we have for sure that it's negative, um, this point here is 40, and everything that is such that the real part is greater than, which is basically this, because the magnitude of the real part is going to be feasible. Now, this this region here represents a case where we have the overshoot less than 9%, and this case is the case where settling time is greater than is less than 0.1 seconds. Now, how would you design a system that matches both of these? Of course, there's a case of and, which means this behavior must be satisfied and this behavior must be satisfied. And now if I bring them together, what is the region that is overlapping? Essentially, this region is where your pole must be so that your medical device behaves in the way that it should. So when it's within this cone, the overshoot is met. And so left of this line, the settling time is met. And so to have both those criteria met, it is this region that is desired. Okay. Um, so that was an example of system design. Now, how does this apply to our control system discussion? To do this, we're going to be using transfer functions quite a bit again. So here we have your transfer function for the system that you're controlling, that is going to be given by gp of s, which represents the plant transfer function. So this is essentially what we encircle as a system. For example, when we were looking at this, we said this here is a system, there's an input to the system. And also, to be complete, this here is the output of the system, is how is x of t changing. In this case, the system is this. So that is the plant. Now, an input to the system is this here, that is u of s. And the output of the system is, of course, your system response, which I'm going to denote as y of s. What is the input? You can give me some examples, or if this was a live lecture, inputs would be something like a force or a torque, maybe some flow of water into a system, maybe the temperature of the ambient air, whatever it is, these are inputs to a system. Outputs are things like the position, the angle. In the example of water flowing in, it would be the height of the water in the reservoir. In the case of temperature, it would be the temperature of whatever is the component you're measuring, and so on. Now, the objective of all of this is we want y of s to follow r of s. What is r of s? That's the reference. This is what we want the system to do, how we want it to behave. Okay, this behavior or this objective is called reference tracking. That is, we want our system to do exactly what the reference is telling it to do. Now, where does the control system feature in this? The control system can create an input to give the transfer function so that the output matches the reference. Okay. The crudest way of looking at this is to have just a control system here, which is acting onto this over here. This here is the controller given by GC of S. Is the control system, which is generating the input to the system. So it's generating the force or the torque or maybe the voltage or the height or the water flow, whatever it is. Of course, there's also a transfer function. So there's a transfer function, there's also going to be a transfer function. And that transfer function is such that it takes the reference, R of S, and it converts it into the input to a system, U of S. So the reference would look something perhaps like this. And in the Laplace domain, this would be the signal that's coming in. For step function, it would be 1 over, in this case, maybe R naught over S. That is the input that's coming in. The control system now takes that input and converts it into a force or a torque or whatever it is, and then gives that to the plant so that the plant can then provide an output as Y of S. Now, this Y of S being identical to this is the objective of reference tracking. In an example as I've shown earlier, perhaps what you would need to do is create a force that looks much higher first and then it kind of drops down like this so that your system can behave in this way. Or maybe you would have some oscillations that have to cancel out the oscillations in the system. But that creation of this input that defines an output that matches this, that is the job of the controller. Let's now look at some of the aspects of just this layout. From simply the aspect that these are transfer functions, you essentially have that R of S times GC of S is equal to U of S. You multiply this with the transfer function, you get this as the output. You then have Y of S is equal to GP of S times U of S, the planned transfer function times U of S. And we have that U of S is equal to R of S times GC of S. Now, what is our entire objective here? We want Y of S to be equal to R of S. Then what does that mean? R of S is equal to GP of S, R of S, GC of S. Of course, GP of S is an aspect of how the system is developed, so we can't really change GP of S, but we can change GC of S because what you're trying to do is develop that control system. So if you divide by R of S, we then get GP of S times GC of S is equal to 1, or I can write GC of S is equal to 1 over GP of S. So if we do this, then we achieve the reference tracking. In this extremely simple case, where we have just the reference coming in, we have the control system, and the input from that, the output from the control system is the input to the plant. That gives us the output. If we do GC of S is equal to 1 over GP of S, then Y of S is going to be equal to R of S. Let's do an example. If GP of S is equal to 3 over 6S plus 1, then what is GC of S? This is simply going to be the reciprocal of this, which is 6S plus 1 over 3. If we now put Y of S is equal to essentially GP of S, R of S, GC of S, then you will get Y of S is equal to R of S, because this and this will cancel out. Now, this is a very, as I mentioned, rudimentary form of control. In fact, this is called open loop control. Because we make a lot of assumptions. One, we assume that we perfectly know the plant transfer function, which is not always true. For example, the mass of the spring damper system might be different from what was measured because of wear and tear. And so that mass might change. Maybe the damping fluid has escaped the damper and now the damping coefficient has changed. Or maybe the spring has rusted and is starting to creak and that changes the spring constant. Or maybe this in itself was not an accurate representation of the system and instead you needed to have had something that was more complicated, perhaps like this. But we instead defined it in this way to make life easy. And because of that, your plant transfer function is not really true. So all of these things are possible in an open loop controller. So if you define a control system purely as an inverse reciprocal of the plant, then those uncertainties in the plant model can cause you to have an YFS that is different from RFS. Because life would be quite simple if we had exactly the plant model at all times. Now that is a very complicated task. We're not going to look into that. There's another problem, which is that the input that is being provided by the control system is not wholly the input coming to the plant transfer function. In fact, there are other inputs that are coming into the system. These are called disturbances. Okay, so let's say that you have a cruise controller and your cruise controller is now trying to make your vehicle drive in on a straight path is trying to maintain a speed of say 70 miles per hour. But the fact of the matter is that this straight line, it moves over some hills and dips. So if you're not able to account for the fact that the slope in your road is changing, so even though the vehicle steering is in a straight direction, the road might be undulating like this. And so the slope at this point, slope at that point is changing. And those are completely outside of our control and they come in as disturbances to the system. If your control system is not compensating for that, when the vehicle is going down the slope, its speed will increase. And when it's going up the slope, the speed will decrease. But the control system has no idea about these disturbances. Can you think of any other such disturbance? Let's consider the case of lane keep assist. Now your vehicle is driving on a straight uh, road and you're not providing any steering input, and you know that the lane has to keep, it in this straight path. And so if your control system doesn't care about anything else, then it'll have the steering set in a way that it's going to drive straight and call it an end of the day. But the truth of the matter is that there will be wind that is pushing the vehicle perhaps in this direction. You might have noticed as you're driving past a huge truck, you will suddenly feel the vehicle pulled towards the truck. That's because you are instinctively pulling your steering wheel to counter the wind, and then suddenly the truck is creating the shield against the wind. And so now you're suddenly, your input is pulling you into the truck. So those kind of behaviors are disturbances that your control system does not know in case of open loop control. Okay. Let's just look at the case where we do have um, some way of looking at this disturbance. One simple way of thinking about it is to take this output and then somehow allow that to come into your control system. So um, we have our reference signal. This here is the target. We have the output of the system, that is y of s. And we then have a sensor that's picking up that output. Now, the reality is that sensors in themselves have some dynamics of their own. And so they might have a transfer function that takes your y of s and creates an output that is slightly modified. A good sensor will have only a small modification to that output. And now you bring them together. So now this here is your sensor output, and you're comparing that with your R of S to give you an estimation of the error. So this here is E of S, the error. And you now have the controller, that is GC of S. And this GC of S is your control system that is creating a signal that is now coming into your actuator, which creates the input. So the control system is looking into the error between your reference and what is your sensor measured value of the output, and is creating a signal that's going to the actuator, which then creates an output that is some U of S, which is then going into your system. But the problem is that it is being disturbed by some disturbance. This is D of S, and this here is your plant. This is your control system that's creating U of S. There's a disturbance coming in. and these two are added together, and that is what's actually coming into your plant. If the disturbance wasn't there and you knew exactly what the plant was, then all you had to do was invert your plant transfer function to get your open loop control. But now we're looking at a system that can actually look into how much your output is actually varying from the reference, and that variation is measured here with this plus and minus sign. Okay, to go over all of this, your plant is basically the system that we're studying. So if it's a room, then it's a temperature. If it's the temperature is the output. If it's a spring mass damper system, then the position of the mass is the output. Um, if it's a water tank with water coming in, then the height of the water in that tank is the output, and the tank with the water is the system. The actuator is something that creates some controlled input to your system. Now, this control input, if it was a room that you're trying to heat, it'll be the heater. If it's uh, if it's the spring mass damper, then it might be a linear actuator that is creating a force that is being applied to the mass. Um, okay, a disturbance, on the other hand, is something that's uncontrollable and coming into into the system. Something that generally adversely affects the system. For example, if it's a room, then opening the window creates a change in how your system behaves, because now you're allowing air to flow in, and now you're changing how the temperature will evolve. It might be a fan that the user has turned on, and the heater doesn't know anything about this, and so because of that, the fan causes some circulation to then reduce temperature in some regions. Your heater is now seeing that the temperature is behaving differently from what we would have expected. A sensor here is some measuring device that takes the input as y of s, and the output would be h of s times y of s. In this class, we're not really going to look into sensor dynamics as much. And so we can generally consider that this here y of s comes in as y of s itself, and the error is r of s minus y of s. Finally, the controller is the device that generates the control input that is sent to the um, controller, sent to the actuator. Okay, so let's now look at an example. Let's say I have m l square over 12 theta double dot minus mg l by 2 theta is equal to l by 2 f. Here is the equation of motion for an inverted pendulum. I'll actually sketch this out. So we have this here is your inverted pendulum that is on this mass object here. And this is on a sliding rail. And we have this force F that's acting on it. And our objective is to keep this data as zero. That's how you want to um, control the system. So theta r, the reference is equal to essentially zero the whole time. This here is the dynamics of the system. How does F change theta is defined based on the mass, the length of this inverted pendulum. So what is the plant transfer function? That is, what is GP of S? This is just the theta of S over F of S. How is the force influencing theta is captured by GP of S. If you do this, you will get 6 over ml divided by S square minus 6g over L. So what are the poles? In this case, you have two poles. One is negative, is minus root over 6g over L, and one is positive, root over 6g over L. Now this one means that the system is unstable, which, as you know, if you have a theta, it would tend to fall in this way. Now what we're trying to do is develop a force that will cause it to stay vertical. So let's look at an intuitive way to control this. Let's say F is directly proportional to theta, which is that if the force F is some constant times theta, then maybe we'll be able to get it to behave in a way that gets it back to the vertical if the constant is chosen well. So some F is equal to k theta. This will in fact be called a proportional controller. Let's apply this to this system. And let's also make the assumption that the controller and actually actuator are just one. So we ignore the fact that a separate controller and an actuator. Now, if I were to sketch the uh, block diagram, I would have the reference signal, theta r of s, coming in. It's taking the true output, that is theta of s, which is over here. It's measuring that and then subtracting to create the error. It's E of s. And that is now coming into a controller. It's just GC of s, which is creating f of s. And that f of s is going to our plant transfer function, which we saw as 6 over ml divided by s squared minus 6g over l. Okay, so this error is essentially what? E of s is equal to theta r minus theta. Um, so this here is the error in the system. That's how much is theta varying from theta r. In this case, theta r is equal to 0. And essentially, your we have that f of s is equal to um, k theta. And we essentially have then that which is equal to gc of s times this here theta of s, giving us f of s is equal to minus k theta of s. So if we have a control system as just some k times of this, then that k will absorb the negative term. And I'm going to say that f of s equal to k theta of s. So now what is the entire transfer function for this system? That is, how is theta of s changing as theta r of s is coming in? So just look at this as a system. Essentially, this theta of s is f of s times this. F of s is k times the difference between theta r and theta of s. So I will then have theta of s is equal to k times theta r of s minus theta of s times 6 over ml divided by s squared minus 6g over l. And if I were to now extract the theta of s alone and I do the work, I'll have k times 6 over ml over s squared minus 6g over l minus 6k over ml. So what are the roots? You'll have plus or minus root over 6g over l root over 1 minus k over mg. That's just me taking this and reorganizing it in this way. The reason I did that is because now I can look at how it is different from what we had before. Okay, that's if you look at just this, if your force is directly being applied without having some proportionality to the error, then this here was the pole. Now we have the ability to change the pole of the system based on how K is affecting it. Essentially now, if you analyze this, you will have that this here is your original pole, 6G over L minus root over 6G over L. You can now bring this to the left and this to the right based on this here as a factor being multiplied to it. This is how your pole moves. These are the new poles. If K was less than mg, this is how it would look. If instead K is equal to mg, then you will have two poles at the origin. What does that mean? It is a double pole at the origin means you will have an output that is something multiplied with t. So something like 3t or so is your output, which means that instead of your system falling rapidly, it will now slowly fall and it will be a controlled descent. Another way, so this is the case where k is equal to mg, and then a final case is where k is greater than mg. In this case now, your poles have moved to the imaginary axis. And if your k was increasing or decreasing, sorry, if your k is increasing, you will have it moving further away. This is where k greater than mg. This is just by analyzing how the route's position changes. So in both of these cases, your route is, your system becomes marginally stable. In this case, your system double pole at the origin would be 1 over s squared. So yeah, it's some t as the system response. In this case, it would be some oscillating behavior, so it will continue to oscillate. Okay. Um, let's now uh, pause and look at the case where we have some. Give me a minute. Okay. Let's do this problem now, where we do include sensor dynamics. So um, we have a plant given by 16 over s times 0.017 s plus 1. This is the output theta of s. You're able to provide some v of s as your voltage, and your control system is here as c of s. And you want to take the error e of s as simply the difference between theta s and theta r of s. But let's say that we have a sensor that has a dynamic of 0.03. That's simply a gain. Now, how do you convert your theta r of s so that essentially your error can account for just the difference between theta r of s and theta of s when your sensor is creating this multiplication? One easy way to do that is just multiply your reference also with the magnitude of the sensor. That is in this case 0.03. So you just multiply it with the same. And here you will have plus and minus. And now your objective is to make this error equal to 0, because you've now kind of leveled the playing field. Both of these are now multiplied by 0.03. And the objective is that your 2% settling time should be less than 200 milliseconds. and your percentage overshoot should be less than 5%. First, what is the closed loop transfer function? Essentially, theta of s over theta r of s. You can define this if you look at this very carefully. Um, you will have theta of s over theta r of s is equal to 0.48 c of s, that's the control system transfer function, time over s times 0.017 s plus 1 plus 0.48 c of s. Of course, this is obtained by doing all of the calculations here. Um, 0.03 theta of s minus, minus of 0.03 theta of s plus 0.03 theta r of s is equal to this error. That error is multiplied with c of s, which gives you the output, which is then multiplied with this, and that gives you theta of s. You rearrange all of that, and then you get this. What is the steady state theta of s? This is essentially limit s tending to 0 theta of s, which is generally done for a unit step function. So it is like um, setting theta r of s equal to the unit step function, so 1 over s. And essentially we'll have limit s tending to 0, s times this entire thing multiplied with 1 over s as a unit step function. These cancel out. What is this value here? This will be equal to 1 for theta r of s equal to 1 over s. What is theta r steady state? That's basically at time t equal to infinity, this is equal to 1. Because you have set that your input is a unit step function going from 0 to 1. So at time t equal to infinity, the reference has a value of 1. So the error is equal to 1 minus 1 is equal to 0. So in this case, for any C of S, because you can see that it's independent of that, you're getting this output as 1 for an unit step input, and so your error equal to 0. So you've achieved your first objective, which is that your steady state error must be equal to 0. Let's look at the second objective, that is second part A. This much must be less than 0.2 s. Essentially means 4 over the magnitude of real part of the pole must be less than 0.2, giving me the magnitude of the real part of the pole must be greater than 20. Okay, what is the next one? The percentage overshoot must be less than 5%, which basically means 100 e to the power minus pi zeta over root over 1 minus zeta square must be less than 5. This gives me zeta greater than 0.69 or cos phi, that angle will be less than 46.4. Essentially now we have that for our transfer function of the entire system, this is the closed loop transfer function, we have a region in the S-plane that is permissible to us, which is to the left of this here being minus 20. And we have these two rays at an angle of 46.4, which tells us that the region that is permissible is a system with the poles in this region. At this point, we haven't really looked into the controller. Let's say that we do the same kind of controller that we did earlier, which is a proportional controller. Which means C of S is equal to simply some constant K multiplied with that error, gives you the output. So this here is I'm going to call it Kp for proportional. Then this closed loop transfer function, which is essentially a transfer function from theta to reference, is now going to be, and I'm just replacing the C of S with Kp. What are the poles of this system? You will get minus 1 plus or minus root over 1 minus 0.033 Kp over 2 times 0.017 if you do the calculations. And what this means is now for our closed loop system with a proportional controller, these are the roots. Now these roots must be in this region. Okay. So what is really determining the position of the roots is this guy here. So if 1 minus 0.033 Kp is equal to 0, then you would have two roots at a position of um, essentially minus 1 over 2 times 0.07, so minus 28.24. If instead 1 minus 0.033 Kp were less than 0, then you would have two complex roots because you then have this thing less than 0, and so it will be something complex conjugate pair. That would be underdamped. This here is critically damped. And then finally, if 1 minus 0.033 Kp is greater than 0, you would have two real roots, which is the overdamped case. So everything really depends on 1 minus 0.033 Kp. In this case, Kp is equal to 30. In this case, Kp is greater than 30. And in this case, Kp is less than 30. Of course, if you have critically damped or overdamped, you have no overshoot, which means that um, if you want to match design requirements which state that you have some overshoot, then it must be an underdamped system. Okay, so for overshoot to exist, it must be underdamped. And we had found that we had this zeta greater than 0.69 defined for us. So if I now write it in the standard form of s square plus 2 zeta omega n s plus omega n square, and we have zeta greater than 0.69, then essentially from the um, from the denominator of this here, which is basically the characteristic polynomial, which is this 0.017 s square plus s plus 0.48 kp, that has to match this. So to get it to the standard form, I'll have to divide by 0.017. So I'll get s square plus 58.8 s plus 28.24 kp. This here becomes omega n square. This here becomes 2 zeta omega n. And essentially, from this we can write omega n is equal to root over 28.24 kp. And from before, we have 2 zeta root over 28.24 kp is equal to 58.8. So this is now combining these two together. Finally, after all of this, we get zeta is equal to this 58.8 over so on. Okay, I'm going to write it 58.8 over root 2 root over 28.24 kp. This must be greater than 0.69. Right, that is the condition that we developed for the design criteria. So then we have zeta greater than this, and if you were to solve for kp, you will get kp less than 62.9. Okay. Um, so essentially, for the underdamped system, we have that kp must be less than 62.9 to meet our design requirements, and the real part of the pole must be greater than 20, so it's in this region. So these two criteria together um, will meet our design requirements. Okay, that was quite a bit. I hope that all of this helps you with your assignment. Let me know if you run into any issues.